Okay, let's get started. Good morning, everyone. Welcome to the RTGWG session. I'm Ying Zhenqu, and I have my co-chair Jeff Tansara online. Say hi. So we have a very tight schedule today. So let's start from the working group status. Jeff, go ahead.
Welcome to Montreal, everyone. Please make yourself familiar with Notwell, and by participating in IETF, you agree that you follow our process and policies. All your contributions are public, and please get yourself familiar with the anti-harassment policy. We don't tolerate any kind of harassments here. There is RFC 7154 and 7776 that talks about that. Meeting tips: if you participate in person, please make sure to sign in or use QR code for the session, which is easy. We do like to get large rooms, so we would like to kind of make organizers know that you're here, you're interested. For remote participants, please make sure that your audio and video is off unless you are talking, and use headphones. And all participants, when you say anything you want to participate, please introduce yourself. Please help us to collaborate on minutes. We've got, as Injun said, very busy agenda today. Please do your best to be in time and don't eat time of others. And yes, we finally publish topology independent TI-LFA, and it's been really long time, hard work. We thank everyone who contributed, who participated, and yeah, it's been a long time. We didn't adopt any new drafts since 123. We don't have anything in editor queue. We've got significant number of drafts that are getting close to working group last call. So with BGP peak, there's more work needs to be done. People, you know who you are. Please do the work. We need you to participate. I'm talking about co-authors. Please work on this. The update to the RRP, we believe it's ready for working group last call. After IETF, we will ask you. The BFD work, I think we are still working on it. The author requested second working group last call to net to cloud. We will think what to do with it. There are some opposition to that as well. Multi-segment SD1, again, post IETF, we will look into starting the process. QS model, good progress. I think it's almost ready. There are some reviews, comments that need to be addressed, but we are getting there. And then we've got some work on egress protection for Service 6 and national routing revive that need to be addressed. Any questions? And if none, we can move to the presentations.
Yeah.
Sasha?
Sasha?
Yeah, I just wanted to say that I have sent my concerns regarding scalability of the SRv6 egress protection draft. Just for it has been sent to the list and also to the LSR, because the scalability there, the proposal as I see it implies distribution of substantial amounts of information on IGP, which normally are not used. That's all.
Thank you, Sasha. And authors, please do address all the comments received on the list. It's an expected part of the process.
Yeah.
Let's move to the presentation if no more questions.
Any other comments? Otherwise, we'll go to the presentations because we do have a full agenda. We want to save every single minute. Okay, let's go.
Sasha, please remove yourself from the queue.
Good morning. I'm Sam Zhang from ZTE. This time I'd like to start from a very specific use case to discuss multicast in LLM. So I present this draft on behalf of our co-author Wei and Xiaohu. So at first, let's see the introduction of this topic. We know that LLM is the abbreviation of large language model, which is the most popular now. Yeah. So we know that the LLM has become larger and larger. So it's more and more hard to deploy the LLM in just one or two GPU or just in one server. Yeah. So MOE is a new architecture of LLM. MOE is the abbreviation of mixture of experts, and it's a new architecture for LLM. So in MOE, only a fraction of LLM's parameters will be activated in one GPU. So in MOE architecture LLM, the LLM will be deployed in several GPUs, and the GPUs can be called as expert. So only portion of the parameters will be activated at one expert. So each time when we want to use the token dispatching, the token will be sent to a set of selected experts to the computation. So let's explain the token simply, in case somebody may not familiar with it. Because if we want to ask question to DeepSeek or Llama or something else, you must input your question, right? And if we want them to do some draft translation, we also need to upload the file to the AI tools, right? So at the beginning, the LM will divide the question or the file into many parts. Each part will be seen as a token. So the LM will execute the token one by one to the selected experts for computation. So by using MOE architecture, it can bring a more cost-effective training and inference method. So it's become more and more popular now. Yeah. So this is a figure of the MOE architecture market training. So you can see that several our mainstream AI tools such as Google and XAI or Mixtrail or DeepSeek, all are used MOE architecture now. So by using MOE architecture, the less GPUs you can use, but you can achieve the same computation result as the previous deployment. So we know that the first business MOE architecture LM has been published in last year. It's Mixtrail, and it has 8 experts. And in Llama 4, though the Llama 3 has been shown here right now, but in Llama 4, there are MOE architecture version now. So in different of Llama 4, you can see 16 experts or 128 experts. And in Mixtrail and Llama 4, only 2 experts are activated at a time. But in DeepSeek v3, you will see that there are 256 experts as a pool. So, and for each token calculation, 9 of the 256 experts will be selected for calculation. So we can know that it's a training for all the models. So this figure is from DeepSeek paper. So this is a gating function in LM. So by using the gating function, the experts for each token calculation will be selected from the experts pool. So we know that because we have so many experts, it can't be deployed just by one server or two servers. So there are many servers need to attend this calculation. So the communication may span leaf switch or even spine switch because we need more server to do it. By using the gate function, tokens are sent to multiple selected experts. We know that it's a typical multicast use case. But we know that the selected experts is not all the same. Even if in one training or inference process, because for each token will be sent to different set of experts to achieve the balance goal. So each time the token will be sent to different experts. And the time used for gating function is extremely short, possibly only a few microseconds. So it's highly dynamic characteristics. So it's his feature. So our work, the motivation of our work is that we'd like to use network multicast technology to assist LM multicast implementation. And so we can achieve two goals for it. And we can reduce the pressure on the source GPU. And also we can reduce the possibility of congestion caused by bandwidth between nodes. So in order to achieve this goal, we have set a meeting in last IETF meeting. So in July, we successfully had the LM MOE multicast set meeting. We have a lot of discussion at the meeting. So the conclusion is that because of the dynamic feature of the token dispatcher, we think that beer may be the best choice to adapt to the high dynamic characteristics of LM. So this is some information about the set meeting. You can get it from these links. And we know that there are still some gaps for this work because we need a modification of application and the transport layers to adapt to beer technology. And also, we must keep the reliability of multicast technology. So we have a specific mailing list, multicast for AI. So you can join the list to share your consideration and the information, and so we can do the work together. Yeah. That's all for today. So.
Any questions?
It's important to add there is related work that's going on in beer and PIM working group that are all looking into kind of problem how to distribute traffic, given that signaling has kind of two components: control plane that's usual multicast, but data plane, the destination subgroup is only known a couple of microseconds before traffic needs to be sent. So it's somewhat different than regular multicast. And there is a list, so please participate, and we expect to see more work.
Yeah. So I have a question about because every time you have a selected experts, right? So they will be very different from every single time. So it's very dynamic.
Yes, very dynamic.
Is beer can beer?
Yes, only beer can do
that
this.
Speed?
Yeah, we needn't the tree building because every time the different experts will be selected. For DeepSeek, 9 experts are selected at one time from the pool.
How can the source node know who is the selected expert?
The source GPU will use the gate function to decide the selected GPU experts. So it's LM implementation.
Okay.
Yeah.
Okay. Thank you.
Thank you. Seems something in the queue.
Wei Qiang, please go ahead. Be brief. Yeah.
Yeah.
Wei Qiang, are you?
Only one token.
We cannot hear you. Your voice is totally breaking up.
Don't use multicast.
Okay.
Okay,
Well, thank you, Sandy.
thank
We'll
you.
go to the next presentation then. Wei Xiang, if you have a question, please send your question to the list. Sung Jian, go ahead. Yeah.
Okay. Can you hear me?
Yes.
Okay. Hello, everyone. My name is Sung Jian from China Mobile, and I will introduce my first IETF draft, which is about a distributed inference network to discuss the problem statement, use case, and the requirements. Please, next page. Oh, I can. Okay. AI is rapidly evolving and changing the internet usage patterns. Here, I have some summarized. First, internet usage is shifting from content access, like web or video, to nowadays AI module access. This brings new traffic pattern and a new requirement for the network to better support AI processing. Just like we did a lot optimization for the video traffic in past decade. A second shifting is the AI interaction. It's shifting from a simple human to module conversation to complex multi-module interactions. As AI inference price decrease very fast, more and more application IoT devices are now integrated with AI capabilities. So it will bring maybe billions or tens of billions concurrency AI inference and very low latency requirements. The third shifting is the AI inference workload traffic pattern. There's a report indicated that in last year, the global internet traffic grew about 17.2%, and in this increasing nearly about 48% the traffic is driven by AI. So I believe this year will be more. So the internet needed to match the AI inference requirements. For the first is billions level concurrent inference, as just mentioned. The second is latency. Latency is not the issue for the chat, but as more and more application and AI robot industrial control or healthcare inference, these require low response time. The third one is enterprise using inference. It needs very high security. They don't want to give the data or module to centralized AI service provider. So an IETF is good at building a distributed network system. So here we propose to use the distributed inference network to natively support and optimize for the AI service. For the users and the applications, DIN aim to provide inference everywhere at edge and with optimized enterprise. And for the AI inference service provider, DIN enable modules to be deployed on demand and efficient at scale. In the draft, we list some use cases. Here is a simple introduction. The first one is the enterprise security inference service. Enterprise may deploy AI inference at headquarters and its branches in different locations can access this inference service through secure encrypted tunnels over different network, including VPN or public internet. Another enterprise scenario is AI IoT equipment inspection or intelligent manufacturing. This enterprise use cases demand both low latency and high security. The second use case we list is edge cloud collaboration inference. For example, small company may buy some AI servers and deploy them locally at the beginning, and they don't need to deploy very big AI infrastructure. They can maintain the core computation resource on premises and dynamically rent additional AI inference computation from cloud during their demand increasing. This hybrid deployment maintains data security and scalability, and also need the seamlessly integrate local and cloud inference resources. The third use case is we call the dynamic module selections, because different AI service provider can different AI service provider can provide a different AI service in different location, different price. So the application can smart routing, and the application needs smart routing and dynamically select a suitable AI module in suitable inference edge based on the, for example, the network condition, the computation requirement, the accuracy, and also the cost. Next one is we call the adaptive resource scheduling. Now we usually use the large AI module, but there are several people already from Berkeley or and NVIDIA report that the small module can also do some jobs very well too, and the small module can reduce the resource and deployed very easier in local or in the edge. So how to combine small module and large module to work together is a use case to reduce latency and total cost. In this pattern, small module processing simple jobs, where large module can handle the complex task. And also another is profiling and decoding separated in different network location. It may enable scalable handling of concurrent session where get low latency without losing any accuracy. The last use case we list in the draft is privacy preventing splitting inference. For application processing sensitive data, the inference processing can be split into different parts and deployed locally and deployed in third-party cloud separately. So nobody can get the whole module or a whole provide inference information. In the draft, we list some use cases. It's not enough. And here we summarized some key requirements for the DIN network. The first is scalability. The DIN should support billings or even tons of billings concurrent inference sessions. The second is inference network should provide low latency, minimal jitter, and extremely low packet loss performance, and isolate between different workload. The third one is security. Security is a must. Compressive protection mechanisms are required to cross the entire network protocol stack, and with very high performance and encryptions. The fourth one is the network should recognize its AI inference session. So fine-grained workload identification and application-aware traffic steering are needed. The last one is network end-to-end telemetry. The telemetry should not only think about the packet latency, the packet loss, but also should introduce the inference-specific measurement like token latency, the token throughput, or inference efficiency. Okay, thank you for your attention. This draft is just the first version, and any comments and contribution are welcome. Thank you.
Any questions? Okay, Thank you for the presentation.
Okay, thank you.
Zhang Li, yeah.
Yeah, can you hear me?
Yes, and you have control of the slides.
Oh, okay. So this is Li Zhang from Huawei. I will introduce the agent networking use cases, requirements, and architecture on behalf of my colleagues. Okay, so the background for this topic is the agent networking era is coming. So with the iteration of large model capabilities and deepening of scenario demands, agents have evolved from single tools to core entities with autonomous decision-making and collaborative interaction capabilities. They have achieved large-scale implementation in the fields such as enterprise, smart homes, industrial internet, and financial risk control, driving the evolution from the human and computer interaction to agent and agent collaboration. So the key enabler for the agent networking is agent connection protocols, such as MCP and A2A and AMP, and maybe some new agent connection protocols will also emerge in the future. So a question is, what can the network do in the era of agent networking? Okay, and so with this question, we draw a picture for the overall agent networking architecture. The architecture can be divided into two layers, the agent connection layer and the physical network layer. The agent connection layer realizes the interaction of general agent applications of different areas. Some of them maybe just connect directly, and maybe some of them needed to connect through the agent gateway. The physical network layer is on the hand, on the one hand, it provides the basic connection for the agents, and on the other hand, it also utilizes the agents and their networking to make itself more smart and more efficient. So we will give some use cases about the agent networking and how the agents networking can make the network more smart and more efficient. Okay, the first case is a bank union agent networking use case. A bank union organization typically refers to a non-profit joint organization collectively established by numerous member financial institutions. For example, with the Visa, UnionPay, and MasterCard, they are all bank union organizations. So for a bank union organization, the IPO auditing is one of their typical services. In the IPO auditing, it first a user need to apply for the listing of a turnover from one application to the Bank Union platform, and then the Bank Union platform forwards this application to the banks. And then each bank performs user authentication and authorization, and each bank then returns the turnover information to the application through Bank Union platform. So in this IPO procedures, as introduced in the last page, it is realized by API-based service calling. It is now realized in this way. The banks provides the API to BOP, and the BOP provides API to applications. So there is a shortcoming in this way, because the BOP need to synchronize the API with every bank and application. which requires a high cost. So, however, this shortcoming can be solved by introducing the agent. The banks and the applications can provide their service through agents, and the agents interconnection replace the traditional API calling. So the standard APIs are not required anymore because they can use natural language. And then we can use the agent gateway to control the boundaries of different domains. And it also enables secure and scalable cross-domain agent interconnection. The second case is the network device agent networking. We have two detailed cases. The first case is fault diagnosed in data center network. The fault diagnosed agent can be deployed in data center network devices to detect the diagnosis faults. Some faults related to links or neighbors can be diagnosed through the interaction with neighbors agent. So in this case, the network device agent networking improves the diagnosis efficiency. And the second case is about the campus network. The network segmentation in campus requires a verification of consistent policy across multiple security domains. Agents residing in firewall switches or where these controllers can collaboratively audit their configurations against the intended policy to identify the discrepancy causing the segmentation failure. So in this case, the labor cost is reduced through the agents networking. And we have the third case is about agent networking between the controller and the network device. We have also two detailed cases. And the first case is about the network performance monitoring. We can deploy a MCP server or agents in the network devices and then deploy a MCP client or another agent in the controller. Then an operator can send a performance monitoring request to the controller. For example, it can say, show me the bandwidth utilization of all core routers. And then the MCP client can returns the information by the interaction with the MCP servers or device agent deployed in network devices. And the second case is network troubleshooting automation. This is similar with the first one. So I think I don't need to introduce it again. Okay, and this page shows our draft submitted to IETF on agent communication. We have more than 80 drafts focusing on different problems, including the use cases and the frameworks and the gap analysis and so on. Okay, and so we think this is just a beginning. We still have a lot of work need to be done in this emerging area. And we also work on for comments and collaborations in this topic. And in the last, I want to say we still have a presentation in the LA Enterprise Site meeting on Thursday. So if you have interest, welcome to join this session to see the more detailed use case introduction. Yeah, I think that's all.
Okay, we have a few people in the queue. AC, please go ahead.
AC Linda Marcus. I have to admit I haven't spent a lot of time with this, but I looked at it and I got in the queue before I saw your draft with all your slide with all the drafts that are related to this problem. But this looks to me to be more, if there is something to be standardized, it's in operations and not routing. Would you agree with that?
I think yes, maybe, but we haven't think fully about which area to do this work. But maybe RTG can do some work on the agent routines or some path selections or forwardings.
Okay, thank you. I'll let others comment.
Yeah, from Huawei, quickly feedback to AC's question. I think there are two use cases, two major type of use cases. One is about the agent gateway that maybe require some routing mechanism to distribute the information related to the agents and applications. The second case is about agent in the devices and the controller. There will be helpful for the monitoring and troubleshooting of the network. It's more related to the operation, right? So there are two separate type of use cases there.
Hi, Rashmit from Huawei Canada. There's some interesting aspect to this. I wonder whether you have looked at the agent gateway protocol to actually see whether you can actually do anything else. The protocol itself is interesting, but at the same time, it's important what we carry in that protocol. What is a summary mechanism? How do we summarize all these agents behind it and basically send the summary information along all the gateways? So it resembles what we did back in BGP time, basically, right? You know, how do we actually carry these information along and basically join the network, basically, and pick up the peers and all that stuff. But I strongly suggest to take a look at the agent gateway protocol and see whether there is anything in there that we can augment. And I'm not sure where the right place for it is, whether it's the routing area, because it's not really routing. And see whether we can find a host for it. There is a talk about a new working group, which is basically going to be hopefully formed for the agent to agent communications. It might be useful to bring, if that working group gets established, it might be a place to actually discuss this type of things. But I'm not sure whether routing is a right place for it.
Yeah. Okay. So thank you for your comments. We'll consider.
David, you are the next.
Yes, sharpening some of the previous questions. I see use cases. I see a whole lot of drafts in this in the presentation. But what do you want the IETF and specifically the routing area to actually do?
I think maybe this is still in the discussion, but I think now we think maybe RTG is an area to discuss this question. We can have a further discussion on the mailing list.
Okay, discussion is discussion. Okay. You will make much more progress if you come with specific proposals of things to do or problems to be solved.
Yeah. Zhang Li, maybe you can answer the questions on the mailing list. And we we need to move to the next presentation. Thank you.
Thank you.
This is this is an informational draft that advocates scheduling network resources for machine learning clusters. It's true that the compute investment for LLM processing clusters is significantly large than what is typically made for the network itself. It's also becoming increasingly obvious that the performance of the network has a significant impact. The on the compute. So what we are advocating here in this draft is to estimate, allocate, and deploy network resources along with the compute resources. The draft proposes uh, to take a holistic view for optimizing the in training and inference job completion times. So the primary purpose for presenting this here in RTGWG is to encourage the community to um, take a look at the problem space holistically, not just focus on tactical congestion mitigation solutions, but also to to look at proactive approaches that would facilitate strategic congestion avoidance. My name is Pawan Biram, and I'll be presenting this on behalf of my co-authors, Kiriti Kompella, Aditya Mahale, and Raghav Bhargava. Um, a majority of the approaches, the solutions that are being discussed for congestion management in ML clusters today are reactive in nature. Most of these tactical solutions, the basic premise is to detect the congestion as quickly as you can and send fast notifications to relevant entities. And you will see a fair number of those proposals discussed today under the Fantel umbrella as well. When congestion events happen, the job gets stalled, it can get aborted. So it's important not just to tactically mitigate it when it happens, but also to strategically avoid it as much as you can. One of the key considerations that comes into play in these tactical approaches is to figure out where to send these fast notifications. Sending it to the P hop or the PP hop is not always sufficient. In an ideal scenario, you would want to send it to a select set of relevant English sources that would take corrective action in a timely manner. As I noted, the proposal is to adopt a proactive approach and schedule network resources upfront. Uh, the basic idea is to identify the endpoints, identify the network resource requirements, and go about reserving the resources for the job at hand. And we'll talk about how that's done in the next few slides. Before we take a look at network scheduling, let's take a quick look at what a compute scheduler offers today in these environments. The couple of popular compute schedulers that are listed here for reference. I'll not go through those, go through the specifics of these. From a takeaway point of view, a compute scheduler would allow you to, it would enable optimal sharing of compute resources among multiple tenants, multiple jobs. It enforces limits, it ensures fairness, and it would also enable accounting. So if you don't have a compute scheduler catering to multiple tenants and multiple jobs, becomes quite tenuous and impractical. So given what we know of compute scheduling, let's look at how we can bring network scheduling into the overall job placement pipeline. The basic task of network resource scheduling is to reserve resources along the pathways between, say, a set of ingress XPUs to a set of egress XPUs. This is done after you've determined the various phases of ML communication, after you've determined the endpoints and the type of communication in each phase. Resources are reserved for each flavor of communication. And once these are reserved, you would monitor resource utilization to see if any adjustments need to be made over time. There are a couple of places where the network scheduling can be brought into the overall job placement pipeline. It can happen when the compute scheduling is done. It can happen when a communication phase is entered in coordination with the CCL. Um, Irrespective of where it's placed, the input parameters for network resource scheduling remains largely the same. The difference primarily lies in how you determine the input parameters like the endpoints and the type of communication that's needed. When we reserve resources, all the transit nodes or the junctions know who the sources are. So if when there is a need to send congestion notifications, there's no ambiguity as to where these fast notifications need to be sent. Network scheduling can also uh, allow for job isolation, which comes into play when you have multiple tenants and you have multiple jobs running in parallel. You could also schedule backup paths for allowing fast recovery. So in a sense, we are trying to mimic what we have traditionally done in T networks with global repair and local repair. Think of it as global congestion avoidance working in tandem with tactical congestion mitigation. Um, Catering to AI workloads isn't necessarily confined to the DC itself. You have to worry about what happens when these workloads start spilling into the DC, into the DCI or the metro. What we are trying to say in this slide is that you could apply the same concepts in all these scenarios with some caveats based on the scenario in play. Um, the, as I noted, the primary purpose of putting this draft together was to discuss the problem space and make an argument for doing network resource scheduling. But the document also talks a little bit about using traditional TE principles for resource reservation and traffic isolation. We do have a construct being discussed in the TEAS working group called DAG-based multi-path traffic engineer tunnel. It facilitates unequal cost load balancing, not just at the head end, but also at every junction that makes up the DAG. So the belief there is that we could use that construct not just for enhancing multipath capabilities in traditional TE networks, but also bring in new TE features into networks like these that are purpose-built for massive amounts of eCMPNS. There is, as Sandy was presenting earlier, there was a multicast angle to it. So there is some work being done to put together a solution, a similar DAG-based solution that would cater to the multicast needs as well. These are early days for the document. We will keep refining the document in the next few weeks. We will also double click on what we mean by network resource reservation, what other resources apart from bandwidth need to come into play. And yeah, as I noted, the primary purpose was to trigger a conversation, make the working group look at proactive approaches as well that could work well with tactical approaches. That's all I had. Questions?
Okay, we have several people in the queue, so ready. Yeah,
Keep
go.
going.
Tal Mizrahi, Huawei. Thanks for presenting this work. When you say scheduling, I assume that you mean a specific time frame with defined times. So I wonder what are the time requirements in terms of accuracy, more or less order of magnitude.
That depends. I mean, depends on the type of the job, the size of the job. If it's a long-lived job, then yeah, obviously you would schedule it for a longer period of time. Even in scenarios where the job is short-lived, if your job is short-lived, you could place the path and twiddle just the the DAG construct that we were looking at. You would place the DAG up front, but you would change the junction bandwidths and the load shares as you deem appropriate. But again, this is a strategic thing, but you would still need to have some sort of tactical congestion mechanism that would work in tandem with this.
So you haven't considered any specific accuracy requirements at this point?
No, we will. I think the next step would be to do some experiments, come back with some numbers, and then make a case for when this would be applicable and how it would be applicable.
And also, I wonder whether this is in any case related to the work in the TVR working group. No. Time variant routing.
I'm aware of TVR, but I don't think there's anything there that.
Thanks.
Zafar Ali, Cisco Systems. What I like to point out is that there are two drafts in SRv6 ops on this same type of work in AI fabric, front end and back end. These are two drafts. And they're based on SRv6. And why they are in SRv6 ops is because there is zero change to SRv6 to do something like this. All the construct already exists. In fact, there is no change required for SR to do this NPTE construct. So I just like to point that out. That draft was presented at last IETF in Madrid. those drafts. So you may want to look at those.
Yeah,
Thanks.
thanks for bringing that up. I mean, this draft doesn't. I mean, it does talk about MBTE as a potential solution, but the primary purpose, as I said, is to let the community start talking about product approaches.
Sure. Thanks.
Jeff, you are the next.
Jeff Tensor, NVIDIA's participant. So thank you for bringing this work. It's important. A couple of comments here. Number one, the clusters themselves, most important property of they're homogeneous. So doing traffic engineering on homogeneous infrastructure makes very, very little sense. It's an expensive operation that brings no results. So it becomes really interesting when you have DCI, and especially interesting when you have optical switches in between that could dynamically change the topology. This is fundamentally needed for this kind of topologies. DC to DC, absolutely. We need to be able to provide much more expensive resources on the one. So I think the focus should be kind of outside of traditional 3-5 stages fabric. It's very fast. You've got full bisection. It's really not interesting to do traffic engineering there. Second comment, congestion control that, highly utilized in this kind of clusters have very interesting properties. It reacts on RTT, reacts on packet loss, on the CN settings. There are really many things. You absolutely need to understand how reservation will interact with congestion control so they don't get to interact with each other in weird ways. That's all on my side. And again, thank you for bringing the work.
Thanks, Jeff.
Yeah. From Huawei. Yeah, I have two questions. The first is, it seems this is like some kind of planning based on the information of the requirements of the application, the connection, and the traffic requirements, right? So what will be the expected granularity of this resource planning and what is the dynamicity expected? Like for how long time you need to update the reservation or the planning of this for this TE traffic reservation, resource reservation? Yeah, this is the first question.
So just like you would, as part of the compute scheduling, you would identify which particular GPUs would be able to cater to, say, that job or shard of job at hand. Once you identify that, the idea is that you would be able to determine the pathways for those input set of GPUs to the output set of GPUs and go reserve resources for that. So it would come down to how big the job is and how you want to place it.
Okay. So the second question is, as you mentioned, multi-tenancy, job isolation, and the resource reservation. I'm thinking whether this is has some relationship with network resource partitioning, like NRP. We discussed in the TS.
I knew you would go there, but but yeah, let's talk about it offline.
Yeah. And the resource need to be reserved on each hop, or is it only like need to planning on the ingress only?
Yeah, so the basic, I mean, if you are talking about a job isolation, then you naturally veer towards partitioning solutions. And yeah, we can talk about how you can
related to the concept, right?
Okay. David, you are the next one.
Yeah, I basically want to plus one Jeff's remarks on traffic engineering. As a traffic engineering proposal, this is essentially inapplicable to a cluster and data center. It is, however, very interesting when you are trying to coordinate clusters across data centers and the metro use case where you've got less powerful devices involved. So I would encourage focusing on that and not spend time on the cluster and the data center, because in practice what people are doing is they're throwing hardware and bandwidth at these problems and then using CPU scheduling to implicitly schedule the network.
Okay. I mean, in the DCI and the WAN, it's a given. We do see lots of folks already using various types of bandwidth engineering tools. The intent here is to enhance those tools in such a way that you would find applicability in the DC as well. But yeah, I understand with the current tools that are available, the point you made is valid.
Yeah, I mean, I would focus on the WAN and doing something really interesting there, and then seeing if the DC people get interested.
Okay, thanks.
Thank you for the presentation. We are already a little bit behind schedule, so let's hurry up. A big background about this presentation, there was a Fantail BOF at IETF 123, where the requirement for network notification was discussed, as well as some use cases. And at the end of that BOF, the BOF chairs did a poll, and the poll results showed there was support for the network, for the notifications, but there were also indications that some people were not clear about exactly what the problem scope is. So that's why the AD sent an email saying, we want the problem scope to be further clarified in the RTGWG working group, because the RTGWG does have the incubation function for new technologies. Hence here the presentation. So we'll have actually several presentations about the notification work. So start from the problem statement, which is the most important one, and the few following ones that sort of test the solution space. We are not to work on exactly solution yet, but hopefully some of the solution draft will also help you to understand the problem. Okay, here, let's go.
Yingzhen, if I may.
Yes, please.
I'd just like to add a couple of clarifications as the AD responsible for the Fantail BOF.
Please.
The mail that Yingzhen refers to actually called out that while the BOF was focused on the notifications itself, one of the feedbacks from the community was, okay, who is originating the notification? How is it used? And all of that, right? So it's up to the working group now to really define the problem statement and possibly cover some of those aspects as well. So it's not exactly the scope of what the BOF was. The second part is the name Fantail itself was on the BOF, and there is no requirement for the working group to continue to use that or this thing. I just want to be clear on that.
Okay, thank you for the clarification. Yeah.
Okay. Yeah. Okay, morning everyone. This is Jedong from Huawei. I'm going to give this introduction about the network notifications problem statement on behalf of all the co-authors here.
Hold on. Try again. Yeah. Okay. On today's. Okay. Yeah.
First, a little bit about the background. I think Yingzhen and Keaton have introduced some of this. Basically, we know that AI training and the real-time services require the network to provide more adaptive traffic manipulation, including the traffic engineering, load balancing, the flow control, and also the protection for the failures. And we believe that the good and timely understanding of the network operational status, such as the congestion status and the failures happening in the network, could help to improve the utilization and reduce the latency and enable faster response to the critical events happening in the network. So there's a need for the network notification related solution in the network layer. As Keaton just mentioned, at last IETF meeting, we had a BOF on Fantail, stands for fast notification for traffic engineering and load balancing. On the BOF, we discussed the use cases and also introduced the concept of faster on-network notifications, and some gap analysis also happened on the BOF. There were very productive discussion there, and we received very valuable feedbacks from different participants, and people showed good interest and willingness to continue this, contribute to this work in the IETF. So as suggested by our responsible AD of the BOF, we will continue the discussion about the problem space of this network notification in the RTGWG. So this document is a collaboration work from a group of people which describe the problem statements of the network notifications. Okay, a quick summary of the use cases of the network notifications. I think this have been presented during both. Just to quickly summarize it. The first use case is AI and the machine learning traffic within the data center. We already know that the characteristic of the traffic is high throughput and low entropy. They are also very sensitive to the congestion and the packet loss in the network. The second case is AI training and the inference across distributed across multiple data centers. So there will be more complex network conditions that need to be considered, and the challenges in the latency and the bandwidth guarantee for the AI training and the inference services. We also have some general use cases about the interconnections among the CDNs, among the data centers, and also the cloud edge continuum is another use case. Basically, all these use cases require large volume of traffic among the data centers, and they are sensitive to sudden change in the network conditions. To all of these above use cases, we believe there's a good and timely notification mechanism to indicate the dynamic network status, like the failure, congestion, utilization, etc., will be useful. In the draft, we summarize the problems with the existing approaches in terms of the notifications. The first problem is if we use a control plane-based hop-by-hop distribution of the network information, it can be quite slow. And another mechanism is we can use the signal of the notification information to the sender, but this will require round-trip delay. Both of this will result in the delayed reaction to the failures or congestion in the network. So what is missing now is a real-time and fast signaling of the network notifications. The second problem is for some notifications, they just carry very simple, just a binary or some threshold-based information. Like for the ECN mechanism, you don't just have 2 bits. This cannot give you enough information to make the precise and fine granular adjustment to the traffic in the network. So what is missing is we need more fine-grained status details to be used, to be signaled in the notification. The third problem is the decision in the several mechanisms. The decision is made only based on the local topology and status of the links. So this can result in suboptimal rerouting and the load balancing. Maybe cannot totally solve the problem, or even sometimes can cause new problem to the network. So what is missing is maybe we need a global or context-aware view of the network so that it can make a more optimized solution, decision and actions. The fourth one is the frequent and high-volume information distribution. Even they can provide plenty of information for the decision, but they can cause excessive overhead and can cause a change in the control plane. So this can also be a problem, even if the information is useful. So what we need is a lightweight and selective notification mechanism. So in summary, that we think the notification mechanism needs to be a real-time, fine-grained, and lightweight, and can be delivered to one or a set of targeting nodes for the optimized decisions and action. In the following slides, in the draft, we described the problem space, what we want to discuss and what we can work on further in the IETF. The first is what kind of information needs to be carried in the notifications. Here we list several of the type of information, and there can be more. We welcome feedback and comments and suggestions on this topic. The first is the notification need to carry the type of the event, like it's a failure or it's a congestion or a performance degradation. This kind of information is very useful to determine what action will be needed by the receiving nodes. The second information is the location of the event. This is also the decision need to be made based on where the event occurs. And the third one is, as we just mentioned, we need more fine-grained information about the network status, like the quantifiable metrics, variable metrics like the utilization, the queue length, the level of the congestion, or different type of delays and jitter, packet loss, etc. This information will be needed for the very fine-grained adjustment to the traffic. The fourth and five are the identifications of the paths and the flows which are affected by the event. So this can correlate the event with the affected traffic in the network and the affected paths. So we think that this is just an example of the beginning of this information analysis. We may need to work on the information model for the network notification so as we can better understand what information needs to be carried in the packet, in the traffic, in the message. Okay, the second problem we want to discuss is the recipient of the network notifications. In the draft, we classify the recipients into two categories. The first one is the nodes that participate directly in the forwarding and the signaling of this traffic. There can be the adjacent nodes or like the adjacent router switches. It can also be non-adjacent nodes, which can help in the regional or global optimization. A traditional way is to send the notification to the ingress. It's also covered here. And another thing is some notifications can be sent to the end host or the edge nodes. The last one is the network controller. It is more about the signaling, but sometimes the controller also needs some real-time information to make the adjustment to the network quickly. On the right-hand side, we list the functions and applications. This is another category of the recipients. They also need a notification to optimize or monitor or perform specific behaviors to the network. Like, for example, the routing protocols, they may need a notification for some update and changes to the decisions, and the traffic engineering element like PCE, the management systems, and also the analytics systems and application services. This is different from the previous category, which is more in the data plane, in the in more instant information and need to make the action more quickly. So we think the mechanism to determine the type and the range of the recipients needs further discussion and consideration. So this is something within the part of the problem space. Okay, the third problem we want to discuss is the delivery of the network notifications. We think that there are different delivery modes which can be used. Like we can unicast the notification directly to the recipient nodes, or the multicast may be used to send a notification to a group of the recipient nodes. And in some cases, the notification can be sent hop by hop along a specific path of the recipient nodes. And the last one is the flooding may be used for the notification in a specific range in the network. The second thing is we may consider to provide some subscription mechanism for the recipients to select the type of notifications they want to receive. So this can reduce the overhead in the signaling and the processing. So basically, we think the mechanism to support this delivery modes need to make sure that the notification is sent to the target recipients within the target time frame, and it can maybe based on existing messaging or transport mechanisms, and it may also rely on some new protocols if the existing mechanism has some limitations. Okay, so this is just the initial version. So we welcome review and feedbacks on the draft to identify whether we already capture the major problems discussed during the BOF. And we also list some points for open discussion here. Like the first one is whether we should focus on the network notification in general, or we focus on the faster notification just. The second point is whether we focus on the network notification in the data plane, or we also consider control plane or management plane based notification in this in the problem space. And the third one is, do we consider the coordination with other layers in terms of notifications, like in the transport layer and in the link layer? So again, we welcome contribution and collaboration to this problem space, and we can work so that we can reach some consensus on the scope of the problem. Thank you. And now time for the questions.
David, you are the first one.
David Black, Dell. Small comment and a bigger one. The small comment is your characterization of ECN is not correct. Please take a look at what's currently being done with ECN over the transport area. For example, the accurate ECN work in the TCPM working group and the L4S work, including dual Q, that has been produced in TSVWG. The larger comment is going to sound like a broken record. The same thing about use cases that I said on the previous draft should focus on the WAN use cases, not the inside the data center use cases. That's where the opportunity is to make a visible improvement. Inside the data center, there's limited opportunity for this. Thank you.
Okay, thank you.
Daniel?
Okay, Daniel Huang, CTE. Actually, when we're talking about congestion control, there's a lot of mechanisms that has been employed between the terminals. So my question is, whether or not does the recipients or the nodes you mentioned in the slides, including the sending host, I mean the terminal, rather than simply the routing networking nodes.
Yeah, you mean this is whether this should be in the scope or not, right? And the host.
Yeah, because from my point of view, if the terminal is not involved into congestion control, I do not think simply the networking notification will work a lot.
Yeah, this may related to the coordination between the different layers. Like if the network notification can work, it doesn't come to the end host because that will have more delay, right? But sometimes they can need some coordination.
Yeah.
Aaliyah Atlas, Google. I do think this has interesting work in it, but it feels like there's a lot of broadening of the problem. You asked on the last slide, focusing on fast notifications, narrow the problem down and then make progress on a narrow problem which is well understood. I much like David, I have some perspectives that I'm happy to share about some of the framing of the space, but narrow the problem to fast notifications, something that can get done small and quickly. I mean, the BFD working group started very small, very targeted, and has been extremely successful. And I think if this work can proceed, that would be great, but it needs to start small and targeted at real solutions. We've got notifications all over the place. Fast notifications in the data plane are the key point to local nearby routers.
Yeah, thank you for your suggestion.
Yeah.
Nitzan Ribbon. Well, the part of the required or notifications is somehow clear. My big problem is that I'm not sure about the practical use of this information. I think we should have examples, explicit examples of what can be done with this information.
Yeah, maybe we can have the examples in other drafts, like a use case. Yeah. Actually, this draft also has a simple example in the draft. take a look and let me know if it works or helpful.
Okay, Yao Liu, you are the next one.
Yeah. I think it's true that the data frame as notification is quite in some use cases. My question is, do you intend to define a generalized notification to cover all the use cases, or define separate mechanisms for each use case?
Okay. Zafar.
Suffer. Just responding to earlier, there was this BOF where the focus was notification only, non-working forming BOF. And the feedback was that what do you will do with the notification? So I think the both things goes hand in hand, because otherwise you don't know what this notification would be. So I think some of this work was done. That what are we going to do? At least we know notification plus what is the action on that.
So do you mean the action should be also part of the problem space, or we just give some examples?
Yeah, at least it should be, because otherwise, if you go back to what was the outcome for the Fentel-BOF was this, that yes, notification is fine, but you should know also something. So I think from that point of view, you are correct in describing the notification as well as some sense of action.
Okay. Thank you.
Jia Yuan.
This is Jia Yuan from China Telecom. From the comments before, I think the notification is very important to, like, I have some really use case to show how the notification can work in WANT, and how is it work, and how is it to make sure the transmission is done successfully. Thank you.
Thank you.
Okay. Please continue the discussion on the list. Yeah, because we have limited time here, and we'll go to Jeffrey's presentation. Thank you, Jeff. You will have 10 minutes.
Okay, so I'm going to present on behalf of my co-authors for this router info advertisement drafts. So there are two pieces of background here. One is Fentel, which Jim just presented. There have been discussions in past side meetings and BOFs, and then as he presented in the problem statement, we need a fast notification mechanism. I'll skip to the next one. So another piece of background is the global load balancing, which is a specific application of this inside the AI data center for better load balancing by considering the utilization of both next hop and next hop links. Here is a quick example here. Both leaf 2 and leaf 3 are sending traffic to leaf 1. If they both choose spine 1, you may get congestion. But leaf 2 choose spine 1 and then leaf 3 choose spine 2, you can avoid the congestion. So this is a very simple example where you can do the better load balancing by considering both local and next hop links utilization. So to achieve this global load balancing, we have two tools. One is BGP signaling of next hop information that Jeff Haas presented in IDR yesterday. Another one is this router info, which is basically a specific solution for Fentel inside this scenario. We advertise link utilization to neighbors, and that is actually extended and generalized from a merchant ASIC vendor's implementation. And so we are going to talk about this router info drafts in the next few slides. It is a UDP-based advertisement to all or some local nodes on a link via link level multicast, or it could be to a group of nodes in the entire network by a set of individual unicast, or it could be to a group of nodes by multicast. We're basically defining a message bus here. We do not do re-advertisement, meaning that you receive the advertisement, you use that information for your local use. You don't simply flood it. You may regenerate new information and send it to your next neighbor, but there's no simple reflooding like in the IGP flooding case. We can do fast and slow advertisements, and we don't define information retention procedures. We don't establish sessions or adjacencies. Basically allows you very simple and fast notification. We use TLV encoding at the very top level for any kind of information advertisement. It could be used for other purposes as well, not just Fantel. In general, we do not try to define sub-TLVs so that the handling and in the case of fast notification is very simple. If you need to add additional information in later, you can simply just define new TLV for that. And that's a new top level TLV. But of course, you could still use sub-TLVs if that suits your purposes. This is a quick illustrative of the packet format, UDP, with some flags, and we allow authentication, and we include the source router ID and the link ID, and then we have repeated TLVs for the information. So as I mentioned, the advertisement can be fast and slow, or slow. It could be on a per top level TLV base. Each of such TLV has a field we call the refresh rate. This also gives the recipient a hint on how long you could keep the information. The advertisement could be as fast as your hardware can handle. This could be sent from the forwarding path, even by the ASICs, however it can be implemented. A receiver can also negotiate with the sender. A receiver may find out he's being overwhelmed. He can ask the sender to slow down. And if we are using multicast for group notification, we could also use multicast groups for different multicast group for different refresh rates, even if it's for the same content. It's all flexible. So we for that GLB application, we defined a few TLVs, neighbor path information that is basically the next hop BGP ID, and we could also advertise link info, flow redirection info, and there is also a TLV for the refresh rate negotiation. I'm not going to get into the details, but this is basically a high level of what this draft does. So we already have 2 rounds of discussions on this draft. The first round was when it was initially published, and then in the main time frame, we had a second round of discussion. I believe we have addressed all the comments. The GLB application is currently supported by 2 vendors based on that IDR working group draft for next hop information, and also based on that ASIC vendor's implementation of both the flooding of the link utilization info, which this draft is based on, and then also the load balancing mechanism based on the next hop information in routing and link utilization. So in summary, this is a very generic, very flexible, and easily extendable solution. I'm pretty confident that whatever our Fantel discussion eventually agreed on what need to be supported, those can be met by appropriate changes or extensions. The draft is extension or generalization to an existing implementation. We want to have a standardized solution, and we're not trying to just stamp that particular implementation. So we want this working group to discuss this, and hopefully we can adapt this work sooner than later so that we can move on with the standardization if we have consensus.
Yeah, I think this draft was presented before the Fanto BOF. Yeah.
Yeah.
So, Kyo?
Hey, thanks. Kevir Patel, Arcus. Two comments. First of all, can you go back to slide 3, please?
Say it again.
Slide 3.
This one or
previous one? Yeah.
Yeah.
Yep.
Okay.
So this behavior that you are trying to standardize is a very silicon specific behavior. Different silicon families across the board don't support this. This is very specific to a certain vendor. I'm hoping you will have your proposal a lot more generic than what it is. And then the second comment is something along similar lines is also going on in L3DL as a protocol. So happy to chat and interact with you.
Okay.
I had trouble following all your
Yeah.
comments because of the audio situation. So I will follow up with you offline. Yeah.
Yeah. Aliyah, please.
Aliyah Atlas, Google. I'm really happy to see this draft. I agree that it is pretty specific to a particular vendor. It'd be really interesting to hear what other options are in the space. I do have some minor technical questions for offline, but I'm really happy to see the work progressing.
Sorry, one quick comment. Not only is this specific to a vendor, it is specific to a silicon for a given vendor family.
For that, I do want to say again that, as I mentioned in the slides, yes, it was extended from that particular implementation, but I believe we made it very generic, and we want to keep it generic, and we are not trying just to stamp a particular implementation.
David?
Yeah, this slide is provides some. So David Blackdell, this slide provides some motivation for focusing outside the data center. If you look at the AI clusters within the data centers, there are other means of solving this one. In particular, what's called the collective communication libraries. Nickel and Rickle are the two that are most common. But this class of problem occurring across data centers or between data centers and edge is definitely interesting.
I'm not sure the CCO has an impact here because eventually the network needs to handle traffic, and when you have the low entropy in the traffic, you're going to run into this kind of situations unless you do the spray and basically require the receivers.
I think I'm going to just take this offline. As I think there's some things about traffic within an AI cluster that are not understood in this slide, and probably not worth diving into that rat hole here and now.
Sure, we can. Yeah, we can follow up offline.
Okay.
Yeah.
Jeff, you want to say something quick?
Yeah, a few words. As working group chair, I very much agree with Kyor's comment. And in order to progress this work here, I would like to see, and authors, I would like to see further generalization of this. It's really specific to that vendor, to that specific model of silicon today, and their ability to support it. So as we work in IETF, we would need to get some input from different silicon vendors to see what's working for everybody, to find solutions that is interworking and make it an IETF way.
Okay.
And as a working group member, back to David and kind of working on Nickel significantly. Nickel is not a real-time protocol. It doesn't have ability to take real-time input and do recomputation, such as PC, right? So Nickel usually it doesn't get signals from network directly. It might get signal from its peers. So I think there's some confusion. Nickel is not meant to receive signaling of such information from the network. It's not wrong level of information. It's not the right layer to treat this information.
Okay. Kale, you want to say something else? Yeah.
Sorry, I'll just take a minute. Keyur Patel Arcus, I actually agree to what Jeff said. I was going to give the same comment as Jeff did. Nickel doesn't do things in real time. Little different than what it is.
Okay. Tony?
Hi, Tony Lee, HP. My understanding is that Jeffrey is not proposing that we standardize GLB. He's proposing that we use that as input and do something better.
Okay.
Right, and the basic message bus for whatever you can do and you want to do. Yeah.
Okay. Please continue the discussion on the mailing list. I noticed there is also a lot of interesting chat in the chat. So please make people interested in this topic, please make sure you also look at all those discussions happening in the chat. Thank you for the presentation, Jeffrey. And we'll go to the next one. And you will have 7 minutes. Yeah, we are.
Hello, everybody.
Generous.
I'm Xiaomi from ZTE. This presentation is for proxy for congestion notification. First question is, why fast CNP? CNP means congestion notification packet. Common CNP is sent to traffic sender by traffic receiver and triggered by ECN marking at a congested network node. But for the scenario described here, 2 data centers are interconnect by long-haul OTN connection. It takes 5 microseconds for transporting 1 kilometer, and which means 1 millisecond for 200 kilometers. It's not negligible. So we need fast CNP. Fast CNP is sent to the traffic sender by the congestion node directly by detecting congestion. It will not wait for the receiver to send the notification. Second question, why fast CNP with proxy? There are mainly 3 reasons. This picture shows a similar scenario with last one, but 2 data centers are connected by IP1, not OTN connection. But the logic is similar. First reason, without proxy, congestion node needs to know what kind of congestion notification message is spotted by traffic sender. Reason 2, without proxy, congestion node needs to know the mapping table between source QP and destination QP in RockV2 network. And the RockV2 network is currently very popular, so we need to meet the requirements from RockV2 network. Reason 3, without proxy, when one P router gets congested, in this picture, P router is intermediate node in IP1. The congestion node cannot send a congestion notification to the traffic sender directly because the traffic sender is outside IP1 domain. So we need a proxy node. So how fast CNP with proxy works? This scenario is AI training across 2 data centers connected by OTN devices. First step is to select a proxy node. In this scenario, leaf switch within data center is selected as a proxy node. Step 2, the proxy node need to advertise the mapping table between the proxy node and the traffic sender. Step 3, once detecting congestion, a spine switch, the congestion node looks up the mapping table and find the proxy node, the leaf switch. Then it sends congestion notification 1 to the proxy node. Last step, once you receive congestion notification 1, proxy node sends congestion notification 2 to the traffic sender. So I want to highlight that IGP, BGP extensions and congestion notification 1 are standardized in this draft. This is another scenario to show how fast CMP with proxy works. It's massive data sync across 2 data centers. Data centers are connected by IP1. So the process are similar to last one. And in this scenario, we have 2 proxy nodes. One is PE1, another one is a leaf switch within data center. Next steps are small review comments. Thank you.
Joe, yes.
Joel Halpern with Ericsson. On the one hand, we're hearing we need really fast notifications. We need to respond really quickly. We're talking about events which have very short lifetimes. Congestion comes and goes. It's not like, oh, I'm congested. I can presume I'll be congested for the next 10 seconds. That's not the way traffic behaves. So now you're talking about congestion notification over long distance networks. I'm not sure how to get the timing to work from that. And now you want to add a proxy node, which is going to process the notification and transform it into a different format. That's going to add latency to this. If the latency problem is the important problem, I can't reconcile these perspectives. I'm confused.
Okay, let's see the test result. We plan to have an implementation on this and test it. Let's see what will happen.
Jeff has a BGP question, since I see you're using BGP as one of your formats. This mechanism is more than 1 hop away sometimes?
Sorry?
Is the proxy sometimes more than 1 IP hop away?
Oh, for that BGP extension, I think I need to make more refinements on the draft. Currently, I just want to give the solution overview about how it works.
Okay.
Yeah.
So if it is more than 1 hop away, you can't use next hop dependent capabilities. I'm happy to help you with this.
Thank you, Jeff. I will check it.
Jay, you want to make it brief because we are running out of time. Yeah.
Yeah, Jin from Huawei. Yeah, I'm thinking if you want to relay this notification to the end host, maybe you also need some coordination in the network layer to mitigate the problem. If you try to mitigate the problem in the network before it can be handled by the ingress, right?
Yes,
so it's not just
that's another solution about like PFC. This solution is about like ECN.
Okay.
In data center, we have ECN and PFC. And this solution is ECN-like.
So they need to work together to solve the problem, right?
Yeah, another one is PFC-like. I have another draft, but don't present today. Yeah.
Okay.
Thank you.
Thank you. We'll go to the next presentation, and you have 7 minutes.
One short comment.
Okay. Can you hear me?
Yes, please go ahead. And you have control of the slides.
Okay, I see that. Hello, everyone. I'm Yisung Liu from China Mobile, and I will introduce this congestion control based on the SRV6 parts. This chapter will focus on SRV6 only, and I will present on behalf of my co-authors. For the SRV6 parts congestion notification, we have 3 challenges. The first one is the in-process congestion control congestion notification in once. So as we know that the traditional PFC relies on the Ethernet multicast frames to propagate the congestion signals. But in the one complex and meshed topologies, so if we use the multicast-based signaling, fails to accurately trace the paths back to the precise upstream SRE6 source nodes. It will trigger incorrect suppression of non-offending offending flows, spreading the service impact to the unrelated health traffic. For example, in the FIG, if congestion happens in the P3 to P4, and if we use a traditional PFC, it may be notify the signal to the P3 or P4 or P3, and it will affect the blue one of the SRE6 policy, and that will affect the unrelated SRE6 policy traffic. The second challenge is that the long latency SRE6 parse. If we want to control the traffic in the terminal, like in the data center, so the end-to-end SRE6 parse span large geographic distances, introducing the significant unavoidable latency. So that will require the congestion signals to travel all the way back to the source. That will result in unacceptably slow response. So we need that the traffic management must be performed directly on the SRE6 data paths in the intermediate node to enable the intermediate reaction and prevent the prolonged service degradation. And the third challenge is that the control overhead at the SRE6 head node. If we want to control the traffic from the on the head node, it will introduce very heavy overhead. A single head node is responsible for managing and initiating numerous SRE6 passes across the WAN, maybe at least hundreds of the SRE6 policy, even thousands of. It will send all the fine-grained congestion notifications back to this center point. It will create a severe processing bottleneck. So we want to offloading the traffic control decisions to the intermediate nodes along the path. That is critical to elevate the head node overload. Okay. This is a simple proposal for this problem, and for when the congestion happens in the P2 P3 to P4, and detect the queue overload. It will send the notification to the upstream node, like the P2. It may, as we think primarily, it may include the seed list and the slice ID. And the upstream node, like the P2, firstly, will attempt local traffic control. If it cannot reduce the traffic rate or pause the traffic, the unresolved congestion signal will propagate to its upstream until the head node. And if the notification come to the head node, it will make the path rebalancing or the alternative path selection. This is the very preliminary message format. We wanted to carry some carry the SRE6 information like the SRH seed list, including the seed list and the slash ID. Also, the queue information, the flow queue size and the flow utilize the ratio. And for the behavior TRAs, including some the action for pausing the traffic or reducing the traffic. So we want to get more feedback from the working group and welcome who interested involved in this draft. Thank you. That's all.
Any questions? Not. Okay. Thank you for the presentation.
Thank you.
And
okay.
Hold on. Give me a second. Start. You have 7 minutes.
Okay, cool. Good morning, everyone. This is Jia Yuan from China Telecom. Today, my presentation topic is for Fantel for RDNA transmission in WAND. So here we go. So first of all, I'm going to say why we're going to do this. With the rapid development of AI service, the demands of AI computing power is much larger than before. A single DC is limited by the space and the power supplied, so may not meet the requirement of AI computing power. So there's a cost-effective way is to use multiple DCs to do the distributed model training. Moreover, on-premise DC cannot meet the requirement of inference concurrency increases. So you can use distributed model inference between the on-premise DC and third-party DC. So all the scenarios mentioned above, we have to face a problem. Like I said before, the RDNA traffic is very high sensitive to the packet loss. So how can we ensure lossless transmission of RDNA traffic in WAN? So there's 3 key points. The first one is the fair repetition, and then the congestion controls and the load balancing for network state changes. So how can we solve this problem? There's a first solution is the fast notification for terminal-based lossless RDNA transmission in WAN. For fair repetition situations, when the P nodes detect a local link or node failure, it will collect information and send the notification to the ingress PE. And after ingress PE receive the notification, it will react, do something according to the situation. Like if you have the backup path, reroute the traffic to the backup path. If you have the multiple backup paths, you can just update its load balancing policy to fully use all available paths. For congestion controls, like it's very similar to the fair repetition, but this time the P nodes not only send a notification to the ingress PE, but also send a notification to upstream P nodes to reduce the transmission rates of corresponding traffic. For the load balancing for network state change, that's the most simple one. You just the P nodes just collect the information if there's available bandwidth increases, and send the notification to the ingress PE to update its load balancing policy. To achieve this, we have defined two packet formats for notification. The first one is ICMP with 6-based notification, and the second one is UDP-based notification. Both of them, we have defined the A-bit identifier for the purpose of notification. So we can not only notify the congestion concerns, but also the failure protection and link stage. So the foremost message body needs further discussion to ensure both fixed critical information and good extensibility. So that's all for the first solution. Also, we get the second solution is a credit-based flow control based on RSVP for IDNA transmission in one. For this solution, first of all, device in ones need to transmission initialization and specify the mission ID before it starts transmission IDNA. And the device receives this notification, it will send the initial credit value, which is equals to the buffer reserved by the device for the mission to the previous hot device. So when the transmission is start, the device in ones are going to say they separate. Every device in the past will receive the packet and feedback the new credit value to the previous hop. Just like feedback, just like receive the packet and feedback, receive the packet and feedback over and over again until the transmission is complete. When the buffer is almost full and cannot receive more packet, the device will send a packet which is credit equals 0 to notify the previous hop that I can't receive more. Just reduce your transmission rate. Thank you. So after all IDNA traffic transmission is completed, the sender will send the transmission finish message, and the device will release the results resource upon the receipt message. And this is all for the IDNA transmission. For that, we had defined a new credit-based formal control for the RSVP. We defined a new message type in RSVP protocol and in order to adjust transmission rate through the real-time feedback of device buffer state. So next step, we ask for more reviews and comments. Thank you.
Jeff, yeah.
Jeff has a very brief comment for ICMP. Many host stacks and forwarding planes, inherently rate limit that. So you may find that that is a bad way to carry this information.
Yeah, for that, because with the base is focused on one scenario and the turnout, so only the turnout device will receive the notification. So I think it will not be flat everywhere.
As much as that is a nice idea, it is often the case that transit nodes will also apply different rate shaping to that as well. So it is an obvious place for this type of state to go, but you have a lot of long-standing architecture you'll be fighting to do this.
Well, sorry, I didn't get you.
I will post my comment to chat.
Oh, thank you.
David?
David Blackdell. Credit-based flow control is persnickety enough to get to work. It's already sufficiently difficult. Now you're doing credit-based flow control per flow. That's adding some significant complication to what's already a non-trivial RSVP implementation in the network equipment. I wonder if you understand what you're signing up for.
Sorry, because the audio is a little bit noisy for me, so I can't.
Okay.
David, can you please send your question to the mailing list?
Sure.
Yeah, thank you.
Thank you.
Yeah. because it's Jiayuan's first presentation in IETF, so.
Yeah, as a new participant, yeah, that's my first time. Thank you.
Yeah. I think that closes all the FANTO discussions. People who are interested in this topic, please make sure you look at the chat history. And now we move to the last presentation for today.
Yeah, hi. I'm Roland. This will be quick. This is just a heads up presentation, basically, that I've proposed Kira, which is a scalable zero-touch routing approach. And the motivation for this is mainly control plane connectivity, which is an often looked problem. You may have heard of that Facebook outage in 2021, which was basically due to BGP route misconfiguration, and they locked themselves out of their own control plane. Recent paper by Google also states that more than 50% of their major or largest B4 WAN outages were also caused by control plane failures or problems. And so the objective is that you better not lose control over your network infrastructure. And so Kira tries to provide highly resilient autonomous control plane connectivity, no manual configuration, and also no dependencies except connectivity in the link layer. Supports in-band, out-of-band, or hybrid control plane networks, what have you. Existing solutions do not provide all the features that we want. And Kira is highly scalable, up to hundreds of thousands of nodes. It's zero touch and works well in a wide variety of topologies, be it dense data center or sparse WAN topologies, doesn't matter. Also supports mobility out of the box because it's ID based. And since we need better Kira in every network infrastructure that we want to manage, it needs to be an IETF standard. So to make it more clear, the control plane fabric is created by Kira on the left-hand side, and then you can run any control plane application on top of that, like SDN controllers or your favorite network management box. And on the right-hand side, you have, for example, a traditional data plane fabric that is using whatever IGP you want to use. But in order to configure that, Kira provides the connectivity to do that. There's an internet draft now in its 4th revision, and I'd like to get feedback from the working group, actually, so please comment on the list. And I also want the routing expertise here from that group. And we have running code, so we also participated in this hackathon. So we are currently hacking together that native routing daemon for Kira in Rust. We do not need any special forwarding functionality, so we use NF tables and just plain IPv6 forwarding for that. It's not yet up to what's written in the draft, so we are working on that. And there will be a site meeting tomorrow at 2:45. So if you're interested, please come and get some more insights and ask any questions. That's it.
Okay. Jeff, do you intend to stay in the queue, or it was from last? Okay. Okay. Any question for Roland? No. Okay. Thank you for your presentation. Okay. So that's done with that was our last presentation. Any questions in general? If not, I think we are done for today's session. Thank you for everybody's attention and participation. We'll see you in Shenzhen next time.
Thank you, everyone. Have a good day.